Okay, I feel then that we can start for today. So welcome back again to the week 8 of the Introduction to Fluid Mechanics problem solving session. So again in this week we have mainly focused on the implementation of Bernoulli's equation to various fluid flow problems. As we all know, solving numerical problems or at least learning how to apply these equations help us to consolidate our concepts, which is a very good way of learning. So that's why I guess Professor Chakraborty has extensively focused on solving some different kinds of fluid flow problems involving the application of this Bernoulli's equation. So again, just to recapitulate a bit, this is the okay, this is a standard from the Bernoulli's equation with the following assumption, that is first it is in viscid flow, then it is steady, then the fluid properties are considered to be constant. So here basically we consider rho to be constant here, that is the density, and I'm sorry, I'm missing a g here. And finally, if some certain special adjustment is not mentioned, this equation is only valid between 2 points in the flow field along the same streamline. And again, if the flow is irrotational, so if del cross v is 0, then this equation is valid between any 2 points in the flow field. So this is what we have extensively focused in last week problem solving session also. So again, okay, so before jumping into some numerical problems, I would like to discuss some of the standard from the equations that Professor Chakraborty has discussed, which some different forms of the same equation, of the Bernoulli's equation. Like, as we know, we derive the Bernoulli's equation. Bernoulli's equation is a special case of the Euler's equation, as we take certain assumptions to derive or to reach the final form of the Bernoulli's equation. But since problems vary, we need to know different forms of this equation so that we can apply it correctly. So this is one of such form. This is the standard, I would not say standard, but slightly simplified Euler's equation, which you have discussed in the class. So yes, have you encountered this equation in the video lectures?
Yes, sir. Unsteady form of Bernoulli's equation.
Yeah, yes. So actually, it's the Euler's equation, which slightly simplified. And if you can recall, what are the two assumptions that they have used while deriving this equation? Could you please tell? Like from the Navier-Stokes to this form of the flow of this form of the fluid flow equation, what are two assumptions that they have used?
Inviscid flow and along a streamline.
Yes. This is the flow is inviscid, then only we can reduce the Navier-Stokes equation to the Euler's equation, and the flow is along a streamline, so that we could simplify this term. Okay, so the velocity is along a streamline, then we along the streamline coordinate E escape denotes the normal vector, sorry, the vector along the streamline coordinate, and that's why we denote the velocity vector and the what to say, the vector along the normal vector, the vector along the streamline, we can denote the vector along the streamline in this form. So that's why implementing this, we can simplify this term into this form. Okay, then again, like if we take rho is equal to constant in these above equations, because here we have not explicitly assumed that rho is constant. Okay, rho can still be a variable because we are not integrating here. So once, if we need to integrate, and if we assume that the rho is assumed to be, if we assume the rho to be constant, then we can simplify this equation even further, so that we can finally reach. Is there some? Is it clearly visible, the screen? Yes.
Yes, sir. Visible, sir.
Okay. It was showing some glitch in the computer. Okay, that's fine. So after doing certain integration and taking the assumption that rho is equal to constant, we reach this final form of the equation, which is known as the unsteady Bernoulli's equation. Okay, this is a simplified form, which is a form that is being simplified after taking the assumption that the rho is equal to constant, and we finally, and then we reach this equation, that is the unsteady form of Bernoulli's equation. Okay, then again, just to recapitulate, because this session would be exclusively include the application of Bernoulli's equation in its different forms. That's why it's a good practice to recapitulate some of the various forms of this Bernoulli's equation, some of the special forms. That's why, so that we can have a little bit of idea how to approach different types of problems. So again, this is Euler's equation along a stream in a streamlet coordinate system. So I guess Professor Chakraborty has discussed its derivation, so I will not go extensively through its derivation and just discuss the final form of the equation. So along the streamwise direction, that is along the s direction, so streamwise direction, this is the form of the Euler's equation, and along the normal direction to the streamline, this is the form of the Euler's equation. So is there any confusion regarding these equations? Any confusion regarding the terms? So you can ask, otherwise you can proceed further.
No, sir.
Okay, thank you. So since there is no doubt, we can proceed further. And okay, so as per my knowledge, and as per my knowledge of after attending Professor Chakraborty's lectures, I guess he has discussed these 7 different examples for the application of Bernoulli's equation. So I won't go through them again, but just slightly discuss and ask you some conceptual questions, so that at least I know that you are clear about regarding it. Okay, so I guess initially he might have discussed the time required to empty a tank, like how to implement Bernoulli's equation in this kind of problems, and I guess he would have mentioned the Torricelli's law, right?
Yes, sir.
Okay, then there is not actually a specific name for such kind of laws, but this is what I have seen geometrically how it resembles. That's why I named it a squeezing flow. So basically it means that if there is say this is a flat surface, and this is a flat plate of any geometric shape, like it can be circular, rectangular, square shape. So it has a liquid, between this surface. Okay, between the flat plate and this flat surface, we have some liquid in between, and this plate falls with a certain velocity, and because of this velocity, this plate squeezes the liquid between the flat surface and the plate, and that's why this liquid tries to come out from the sides. Okay, since the flow is incompressible, and like here there is no porosity, so there is no porosity. So the only way through which the fluid can exit is through the sides, and if it's considered to 3-dimensional, then it can also exit from these ends. So this kind of flow, I guess sir has discussed. So this is a squeezing flow. Okay, so yeah, then again sir might have discussed about a siphon, how to implement Bernoulli's equation in deriving or in understanding the working principle of a siphon. So since there's only one student, so Priyanka, could you please explain the working principle of a siphon?
It works on the principle of Bernoulli's equation.
Okay.
In siphon, we in a tank we connect it with a pipe.
Okay.
And there is flow of water from the tank to the other side of the pipe using the Bernoulli's equation.
Okay, but what is the actual working principle or principal use of siphon in our day-to-day life? Like, where do we usually use it? Do you have any idea?
Sir, in solar water collector.
Yes. Yes, you are right. Maybe you have read about it, so maybe I don't specifically don't know about it. So
Yeah, I read about it. That's why I said.
there's no problem. I don't know it, so I'm sorry, but right, there can be this application, but some of the primary application that we usually see in our day-to-day life is like extracting the fluid out of a car engine. Sorry, what engine? Sorry, in tank, a fluid of a uh, oil tank or the fuel tank. From there, if you want to extract some fluid out of the fuel tank for some emergency use, we use the principle of siphon. So what we basically do is, I can check back my notes. So yeah, I guess this is exactly what he has discussed. So what basically do is, we insert a pipe of this form. Say this is our fuel tank, and we want to extract the fuel out of this tank, right? So what we want to do is, we want to have some suction pressure in this region so that the fluid could be sucked out of this fuel tank, right? Say, and to do that, what we do is we try to keep the exit of the siphon as low as possible. Sorry, I'm really sorry. We want to try to keep this height in a certain way so that we can generate a suction pressure in this region. Okay. So once we generate a suction pressure in this region, this will suck out the fuel out of the fuel tank, and we can extract the fuel from the exit, right? And if you would have solved some problems, you have seen that the pressure here is usually negative if it is represented in terms of gauge pressure, right?
Yes, sir.
Yes. So this is what to say, a very basic use of siphon in our day-to-day life. So that's what I guess Professor Chakraborty has also discussed, and that's what I also recollect. But still, since you mentioned about its use in solar collectors, maybe there can be use. I do not recall such thing. That's my mistake. But thank you again. So yeah, so thank you. So you can proceed. Okay. So yeah, now let's discuss some specific examples. So let's discuss our pitot tube. So I'm 100% sure sir has discussed about pitot tube and has explicitly mentioned its fundamental purpose in flow measuring devices. So could you please okay, so sir has discussed about pitot tube, so you know about the working principle of pitot tube, right?
Yes, sir.
Okay, then I guess he has also mentioned about venturi meter.
Yes, sir.
Okay, so given these two things, could you please tell me, I have written the question itself here, so the basic difference between the applications of pitot tube and a venturi meter in flow measuring devices. So what is the basic difference between a pitot tube and a venturi meter? Not in terms of geometry, but basically in terms of its use. Like, why do we use pitot tube and why do we use venturi meter? Yeah, please.
So venturimeter, we use it to measure the amount of flow, pressure. Amount of flow is a flow measuring device. Venturimeter.
Amount of flow, like, okay, there can be various flow parameters. So what is the amount of flow basically? Do you mean flow rate?
Flow rate, sir.
Yes. So yeah, you are correct. So venturimeter we use to measure the flow rate. Then what is the use of pitot tube then?
Pitot tube, we use it to measure the stagnation and static pressure.
Yeah.
I'm not sure about it, sir, but from like whatever we obtain from the formulas, I think like that.
Yeah, you are absolutely correct. We get what we get is the stagnation pressure and the static pressure, but the final use or the basic or the the main use of this pitot tube is to measure the velocity of the flow. If you recollect, I guess sir would have sir would definitely mentioned that we use pitot tube to measure the velocity of the flow in a flow measuring device, say, and we use venturimeter to measure the flow rate. Like, you can you can derive different, okay, you can derive different forms of the expressions. You can say that we can obtain V also from the venturimeter, you can obtain the flow rate from the pitot tube, but the fundamental function or the use of these flow measuring devices, that is pitot tube and venturimeter, is used like, so pitot tube is used to measure the velocity of the flow field and the venturimeter is used to measure the flow rate. Okay, and again then there's orifice meter. So could any one of you please tell me what is the, again, the use of, do you know the, just first of all I want to clear that, do you know the working principle of orifice meter? Is the concept clear regarding the orifice meter?
So isn't it similar to venturimeter?
Yes, it is similar, but its geometry is different. But like, I just wanted to know, like, do you understand, do you know the concept of orifice meter? Have you attended the lectures and like have you seen like sir's diagrams that he has drawn, the equations that he has derived? So do you recollect its like this working principle, like its equations, do you recollect it? Like, that's what I'm asking.
Yes, sir.
Okay, then that's fine. So again, if it is clear, then what was its use again? Like, why do we use orifice meter?
So just like venturimeter, we use orifice meter for flow rate, flow rate measurement. But compared to venturimeter, it is less accurate and less expensive.
Yes. So again, like, since we're engineers and our fundamental task is two of our fundamental requirements is that we want to get our measurements as accurate as possible. That is our first requirement again. Okay, the second requirement is that we want to keep it as cheap as possible so that we can do mass production. But again, since it is, we cannot obtain both of them in orifice meter, so there is a, what to say, there is a like, if we gain something we have to lose something. Like, if we gain the if we can produce the orifice meter in a cheap manner, like, what to say, in a low cost, then again we have to sacrifice the accuracy. So that's right. But again, depending on the use, like where we can just, there can be slight, what to say, slight we can have some inaccurate measurements. Like, we can consider some inaccurate measurements, say some in some factories. Like, if we can say that there can be some plus minus some tolerance values, we can have some inaccuracy in our measurement, then we can use orifice meter there. Since like accuracy is not the fundamental need in that case, we want to have lots of pipes, lots of systems where we need to measure the flow field. That's why we need to have that's why we use orifice meter instead of venturimeter, right? But say in some cases where we want to accurately measure the flow rate, there we would use venturimeter, since the accuracy of flow field is much more important than the cost of production, right? So you will see, like, if you again, like, if you are attending labs in your colleges, or if you are going to do some higher studies or research work, you will see that any devices, or what to say, any lab instruments where you are measuring flow rate and where you want high accuracy, there would be a venturimeter instead of a orifice meter. It is for sure. That's why venturimeter is much more popular in these labs, and in industrial work you can see orifice meter is much more popular because of its low cost of production. So again, I guess since it is clear, then again I guess sir has also discussed the flow nozzle, slightly about flow nozzle, how it is more accurate than orifice meter. So just because of its geometry again. And then again, flow through an orifice, I guess this topic also sir has discussed, right?
Yes, sir.
Okay, so yeah, so just to recollect, for pitot tube, this was the governing equation, where P2 represents the, what is P2? P2 basically, I have not written it, so I could ask. So yeah, what is P2 here?
Stagnation threshold.
Okay, I'm not doing diagram, so I guess you have extensively discussed the diagram in the video lecture, so I'm just writing equations. So yes, you are right, it is a stagnation pressure, and this is
Static pressure.
Yeah, this is a static pressure. Okay, so once we know this value of these two, we can get the value of V, right? And that's why we use pitot tube. Again, in this case also, in venturimeter, we use from this expression, this right hand side is measured from the manometer, right? And then these two are known, this is constant, so modifying our menu, and this is known, the head difference between the in the manometer, head difference between the two levels of the fluid in the manometer. So this we know, and only unknown is Q. So modifying or just playing with this equation, you can get the value of Q. So yeah, I guess I already discussed about CD. I guess this is coefficient of discharge, that is Q actual versus Q theoretical, and in general the value of CD varies from 0.97 to 0.98. And for solving fluid flow problems, you will see that they would either mention the value of CD for venturimeter, or else you can just use the value between 0.97 to 0.98 as per your need. Okay, if it's not mentioned, you can use these values. Like if you just need to mention, right? Okay, just before applying it, you need to mention that I have used the value of CD for this problem. Okay, since we're discussing about CD, could you please tell like why the concept of CD comes into picture while studying venturimeter?
So because there will be frictional loss.
Okay, yes, could you please explain a bit more, like what does frictional law actually do? The frictional laws actually do that requires the use of a coefficient, additional coefficient in the equation. You're right, frictional loss is right, but like how it affects the flow rate. So yeah.
Theoretic,
Yes, please tell.
so theoretical flow rate which we get is higher than the actual flow rate.
Yes, why is it so? Why?
Because of frictional loss, sir. I don't know much. Like conceptually, I don't know much.
No, I guess you're right. Sir discussed in a similar fashion, but I think it is necessary for me to discuss, because I've also okay, since you can see here, I also wrote it in my notes. It is visible, right?
Yes,
Yes,
sir.
yes, sir. So yes, okay. So what happens is that, I guess sir has mentioned this in his lecture, that the actual delta H that we get from the, say, any instrument where the venturimeter is fixed, the delta H that we get between the two fluid levels that in the manometer, it is actually more than the ideal case. Why is it so? Because of friction losses, right? And if we look into the equation, I would say like P1 by rho g plus V1 square by 2g plus Z1 is equal to P2 by rho g plus plus V2 square by 2g plus Z2. Okay, so what happens is that the equation for finding the mass flow rate in a venturimeter that we use, that what we do is we neglect the head loss, that is there is some delta H, yes, we neglect this term while deriving the equation for the mass flow rate in a venturimeter, right?
Yes, sir.
Yes. So what happens is that since we neglect it, the effect of viscosity or the viscous losses is not taken into picture while deriving the equation for the mass flow rate in a venturimeter. Right? The equation that we get, this one, does not take into account the losses that one can encounter because of the head loss, because of the viscous loss, right? So that's why what happens is that since delta H is higher, since delta H would be higher, Q would go up, right? Because this is obviously positive, this term would be positive, like if you calculate it, and this is positive. Since all terms are positive, as del H goes up, Q goes up. This is clear, right?
Yes, sir.
Yes, this is higher because of the viscous losses. This will this in actual case, what to say, uh, in actual case, this would be higher because of the viscous losses. But what we are trying to obtain is from the ideal Bernoulli's equation, and we are neglecting this HL term, and that's why to take into account of the effect of these head loss terms, we need to apply, we need to take into consideration a coefficient discharge term, so that the difference between these two heights, the Z2 minus Z1, could be effectively reduced in a manner that we can obtain a mass flow rate that is almost equal to the actual mass flow rate that we can desire, that we obtain. Okay.
Yes, sir.
Okay. Could you please wait for 1 minute? Okay.
Yes, sir.
Just 1 minute. Okay. I'm back. I'm sorry for the interruption. So yeah. Yes. So again, I would like to try, I guess it was a bit confusing, but again, I would like just to repeat it in a slightly better manner. So what happens is that since we use only this part of the equation, that is the ideal case, to derive this one, so the value of delta S should accordingly be an ideal case, right? It should follow the ideal Bernoulli's equation, that is the value of delta S that we would have obtained if we would have not considered viscosity. But since we cannot neglect that, since we cannot remove or disregard the effect of viscosity, since this is not in our hand, that's why this is beyond our hand, and this will definitely go up and give a mass flow rate that is give a value of mass flow rate that is actually higher than the actual mass flow rate. And that's why that's why the researchers or scientists or fluid mechanics researchers, what they did is, after some certain rigorous experiments, they found a value of a coefficient that would try to compensate this additional rise in delta H, so that we can get a value something that is close to the actual mass flow rate. And that's why we need an additional coefficient, that is known as the coefficient of discharge, so that we can approximate the actual value of the mass flow rate. Is that clear?
Sir, just one doubt, sir.
Okay, sure.
So here in this case, we are measuring the delta H value.
Yes.
Like theoretically, like we solve the problem of manometer, we are using it like in the problems.
Yes.
We're solving problem.
Yes.
But if we are if we are in the lab and if we are measuring the flow, there in the manometer, the height, we are measuring directly the difference which you observe in the manometer. No,
yes. And that's why it is higher. It is higher than the theoretical case. If it would have been the theoretical wave delta S, then this value of Q would be right. Okay, then the value of Q would have been correct. But since the equation is theoretical, but the value of S that we get is actual, that's why we get an overestimated value of mass flow rate. Are you getting it?
Okay, so CD value which we are using, only it is for theoretical purpose, not for the lab purpose.
No, it is for the lab purpose. See, I'm sorry if I was.
No,
okay, please.
No, sir. If I'm directly measuring the delta H from the manometer in the lab, then the Q which like after substituting, the Q which I'm getting is the actual flow rate, no, sir?
No, it will be overestimated. Why? Because see, in this equation, if we want to solve the actual case, we should have considered a value of head losses, right? Which we have not considered while deriving the equation. Have you considered a head loss term while deriving the equation for the flow rate in a venturimeter? Have you considered this term?
No, sir.
No, right? And that's why this equation that we get, it is a theoretical equation without considering the effect of viscosity. Is it clear up to this point?
Okay, sir. So the problem lies in the original equation.
Yes. The problem is in the
Okay.
equation. It is a case that the equation is theoretical, but the delta S that we measure, it is practical. It is an actual one that gives an overestimated value. And that would
Okay.
increase the Q, which is not actual. It will give a theoretical value that is not actual, right? It is not correct. And since we want a correct value of Q, we multiply it with a certain coefficient that reduces the or compensates this additional increase in height, so that we can get the actual value of mass flow rate. Volume flow rate.
Okay. So one more doubt, sir, regarding the head loss.
Okay.
Like generally, like in the pipe flow problems, we
Yes.
usually say that there will be head loss.
Yes.
So the flow rate, it will reduce the flow rate. So correct me if I'm wrong, sir. If I take a pipe,
Yes.
then inlet I will be giving like Q1 amount of water.
Okay.
So at the exit, the Q2 amount of water will be less because of head loss.
No, it won't be less. It would be the same. The thing depends is how you're pushing the water from the inlet to the exit. Okay, you need some force, right? You need some energy to push the flow from the inlet to the outlet. Okay, right? So what happens is that since you want to have a same mass flow rate, okay, the same mass flow rate at the exit, what you do is you apply some additional energy to the in terms of a pressure gradient that we call, that overcomes these viscous losses, so that the flow can be pushed from the inlet to the outlet. The mass flow rate never changes. The mass flow rate would remain same.
Okay, so generally, like in the pipe, the water which we get through pipes, underground pipes.
Okay.
So will they be using any additional device to increase the energy?
They need to pump the water, say like in what case you are asking, like some oil pipes or what?
No, sir. Generally, like usually it is mentioned that usually it will be mentioned like in a class and all, that due to head loss, there will be some loss in water.
Yeah, there would be
amount
some.
of water.
Yes. No.
So
Okay. Yeah.
So this is doubt, sir. I'm not sure if I'm correct, conceptually correct or not. I just like it just popped into my head that in the pipes and all, like for example, the municipal water pipes, which we get,
Right.
there will be frictional loss.
Okay. Yes, there will be frictional loss. Yes.
So due to frictional loss, there should be like as per the like whatever we saw, there should be decrease in the amount of water at the outlet.
Yes. There would be a slight decrease. See, what we can obtain is like the velocity of the flow field may decrease, right? The velocity of the flow may decrease. So this would say it is a nice question. Okay, say what does the volume flow rate depend? Say the density is constant. So what does the volume flow rate depend upon? Sorry, Q is equal to
area and velocity.
Okay, so you're right. Since there would be some losses, and since the area is constant, what would decrease? That would result in a decrease in the mass flow rate. It is
velocity.
Yes, the velocity of flow would decrease. Yes, you're absolutely correct because of this. But since you can say in a sense that say I have pumped the water that actually comes in our municipality is basically from a overhead tank, I guess. So where they store the water. So once so if they store the water, if the water is pumped, say the water is pumped at the inlet with it had some certain velocity, say v equal to 5 meter per second. It's just a random values, okay, don't take into consideration. And a is say 1 meter square, okay. So you can think in this manner that and q say would be equal to 5 meter cube per second, okay. So you can say that this amount of fluid is pushed inside the pipe, say for and it took around say 5 seconds, say 5 meter cube. Again, don't take this values, okay. I'm just trying to give a vague understanding, okay. So it took t equal to 5 seconds for this amount of volume flow rate to pass through the pipe, okay. This volume of water took this amount of time to pass through this pipe. So what we can observe is that we may obtain the same amount of water at the exit, right. We would obtain 5 meter cube, this 5 meter cube volume of water at the exit, but it would say it would take around say now 8 seconds to fill the 5 meter cube water, 5 meter cube volume of water at the exit. Are you getting an idea?
Yes, sir.
Yes, the volume of water would remain same, but its flow rate would decrease because of what? Because the velocity, yes, friction loss, that has caused the velocity of the flow to go down, right?
Yes, sir.
Yes, the velocity of flow will go down. The mass flow will remain constant, right? The mass would remain constant. If we had 5 meter cube of volume of water at the inlet, the outlet will also have same, but the time required to this amount of water to pass through the exit would change according to the frictional losses, right? But the amount of water would remain constant. There is no loss in the amount of water, because you initially asked about amount of water, right? It would remain the same. It would not change. The flow rate may decrease, but the amount of water would remain the same. Is it clear?
Okay, so there's a difference between mass flow and flow rate.
Yes. No, don't take in that sense. I'm just saying about mass, and I'm just saying in the sense that by the concept of mass conservation, right? The water that is came through from the inlet, that amount of water should also go out from the exit, right? This should remain constant no matter what. But the volume flow rate of this in this case would it may vary because of the frictional losses, right? Volume flow rate may vary, but the mass would remain the same. We cannot say in a sense that the mass of the water that is coming out of the exit of the pipe has reduced because of the frictional losses. You cannot say like that. You could say is that flow rate has decreased because of the mass flow rate, because of the frictional losses, not the mass. Okay.
Yes, sir, somewhat understood. I will.
Okay, again.
I will think about next class. I will ask again, sir, if I have doubt.
Okay, see, mass flow rate is what? Mass flow rate will basically mean m dot is equal to, sorry again. In this case, m dot would be equal to rho VA, right? And rho for water is, for at least for general purpose flows, would remain constant throughout. So that's why we do not consider mass flow rate. Since rho remains constant throughout the flow field, we just take into consideration the volume flow rate. What I'm trying to say is that, okay, just last try, okay, you can ask again in the next class. I'm just saying is that if 5 meter cube of water, or in general, more simple, if 5 liter of water enters the inlet, 5 liter.
So 1 second, sir.
Okay. Yeah.
I will ask okay, the main doubt which I have in this is what I thought was that since the flow I thought was that since flow rate is decreasing, water will get stored somewhere in the pipe.
No, where does it get stored? There is no storage mechanism in pipes, right? At least in municipal.
No.
There is no storage device. It will come out, but it will take more time to come out of the exit because of the reduced flow rate. It won't get stored. Where it would get stored?
Okay, that was the doubt I had.
Yeah. There is no. It won't get stored. If storage is the case, then why to take into consideration the frictional losses? Even if there would be no frictional losses, and if you are saying that water would have got stored in the municipal pipes, then there's no requirement or role of frictional losses to reduce the mass flow rate at the exit. Even if there's no frictional losses, and if you're saying the water is getting stored within the any section of the pipe, then it will get eventually stored, right? There's no requirement of losses because of viscous effects, right?
Yes, sir.
Yeah. So viscous effects come into picture since it reduces the effective, you can say, mass flow rate also, volume flow rate also. Rate, mass flow rate, volume flow rate, this rate term is very important. Because it takes into consideration the effect of time, right? So the time required for this amount of water to come out of the exit increases because of the effect of the viscosity, since it reduces the mass flow rate or the volume flow rate. Is it clear? Since you're only there in the class, you can ask, there's no problem. After that we will directly approach to the question and answer. So I want you to be clear.
Yes, sir. Somewhat clear, sir. I didn't. Yes, sir. I think I should take into account that flow rate and flow is different.
Yes, it is different.
Okay.
You need to first see, for solving any fluid flow problems, you need to take into consideration the mass conservation, the momentum conservation, and the energy conservation. These three things would be conserved and should be conserved in any fluid flow problems. And the moment you told me that the mass of the water is reduced at the exit because of friction loss, then only I thought that this approach is wrong, because mass cannot be reduced. Mass had to be conserved. But there can be reduction in the mass flow rate. Okay. There can be the Q exit can be less than Q inlet. Q, okay. M exit is equal to M inlet. Since there is no storage term in this case, since there is no place where we are storing water, the water that comes in the inlet goes out of the inlet. So that's why this is constant. This would remain constant. I should remove the this rate term also here. Okay, I'm sorry. Yes. So this would remain constant, but this may happen. Why? Because this again, it is V exit and A exit equal to V inlet, A inlet. So V inlet may be higher, say 5 meter per second, and V exit maybe it will be reduced, say 4.5 meter per second. And since these two areas are the same, basically, which is same in at least in our municipal pipes, so since the velocity is reduced at the exit because of frictional losses, that's why the volume flow rate has reduced at the exit. Is it clear?
Okay, sir.
Yes.
Now I got it, sir.
Yes.
Like,
Yes.
I thought I got confused with the flow rate and that mass flow, sir.
No, it is same.
After you clarified, I got it, sir.
Yes, it is just one more row. If you add, this becomes the mass flow rate. Okay.
Okay.
Yes.
Okay. I thought the mass is also not conserved. That is where I got the doubts.
Mass has to be conserved, right? This is a fundamental principle of any fluid mechanics problem. You need to take into consideration mass conservation. Okay.
Okay, sir. Thank you, sir.
Okay, sure, no problem. Okay, then again, orifice meter. Okay, I think we should not. I will just ask some concepts, whether you are clear or not. Then, if you're in doubt, we can discuss. So, do you know why we are using the concept of this coefficient of velocity in the case of orifice meter?
Because there is difference with the velocity.
Where?
In theoretical and actual case. Is it due to vena contractor?
Yes. You need to use the term. Yes, the term vena contractor. Yes. It is because of that. So that's why there is an additional use of this coefficient velocity to correct that, so that we can get some correct. I forgot to mention the. Do you know? Okay, I'm sorry, I didn't mention the range of V actual and V theoretical. I also need to look into it, but I guess it is around again 0.65 to 0.69. I guess it is in this range, but I have to check it. So I'm sorry again. Okay. And again, we use orifice meter to find the volume flow rate. So again, this equation is like what to say, very cleverly modified in a way that we take into account the velocity at the orifice meter instead of the vena contracta by manipulating the governing equations, and have two coefficients instead of one. One is the coefficient of velocity and one is the coefficient of contraction, so that we can obtain, since because see we don't know the area of vena contracta, right? And what we know actually is the area of the orifice meter, so orifice. And since we want to obtain the mass flow rate, the help of the values that we know, and since this is the value of the orifice that we know, that's why we want to manipulate the equation in such a way that we get rid of the area of the vena contracta. And to compensate that, we use a coefficient that is known as the coefficient of contraction, which generally has the value of again I didn't mention, I'm really sorry. So this I need to know. Okay, I will clarify this in the next class if that's fine.
It's fine, sir.
Okay, basically because since we can see that the product of the coefficient of velocity and the coefficient of contraction would give the coefficient of discharge in the case of orifice meter, whose value usually varies from 0.65 to 0.67. Like this one sir has mentioned, that's why I also recollect, but these two I need to check. I'm sorry. So this is fine, I guess, right?
Yes, sir.
Okay then, do you have any doubt? Because now I would like to directly jump into the problems. Then okay, I guess we can jump to problems, and if you have any doubt, we can just then ask while solving them.
Okay, sir.
Okay, thank you. So this is the first question again. First question itself is the squeezing flow. So yeah. Okay, I will read the question. A liquid layer separates two plane surfaces as shown. These are the two plane surfaces. The lower surface is stationary and the upper surface moves downward with a constant speed v. The moving surface has a width w and perpendicular to the plane of the diagram, where w is much greater than the length. Length is mentioned here. The incompressible liquid layer of density rho is squeezed from between the surfaces. Assume the flow is uniform at any cross section and neglect the viscosity as a first approximation. Okay, so this is a diagram. Choose the correct expression for the x component of velocity u in the gap between the surfaces. So you need to find the value of u in this case. So I guess this is quite similar to the first problem that we solved or the previous problem solving session. So I guess just the difference is that there was a mass flow rate from below the surface because the surface is porous, but in this case it is not porous, it is a solid surface and fluid is squeezed out from here. Okay, so you need to take into consideration and use the similar equations and try to obtain the value of u. Is the question clear?
Yes, sir.
Okay, just try to solve and see how what's the value. Yeah.
Sir, B.
B.
Yes, sir.
Okay, let me check. I also don't know. So you say B. And could you tell how you approach the problem?
Uh, Sir, the mass conservation, sir.
Okay.
The volume of water being pushed is should be equal to the volume of water that is being squeezed
Okay.
out.
Okay. Help me out. The equations. Just use A1 V1 V2 V2. Right. Is it so? Uh, where have you used the
Yes.
control volume here? Is it this?
Yes, sir.
Okay, so could you tell me the equation? What would be A1? What is 1 and 2? 1, I guess you have taken this one.
The top plate.
Okay, 1, and here it is 2, right?
Yes, sir.
Okay, so what is A1 then? W into X, right?
Yes, sir.
Okay, and V would be V, then A2 would be, I guess, B into W, and no, sorry. Okay, and V2 is this unknown, say it is U, I've taken it U. Okay, then W is cancelled, so you get U is equal to Vx by B. Is it what did you got, or is it different? You get an additional 2 term. Why is it so? Like, or am I have I done something wrong? Yeah.
I consider that water is flowing out from two sides, so I multiplied by 2, sir.
Where? Here.
For the two A to V2.
This one, na? Yes.
Yes.
But again, if you're considering the control surface to be in this form, then how can you assume that water is going out from here? Right? The flow is symmetrical between this line, right? So there's no flow out of this plane. If you consider a control surface in this way, if you would have considered it in this manner, then it is fine. But right, then this is fine. Then you need to consider x in if you are considering this x, then you need to consider 2x instead of x.
Yes, sir.
Okay, but since you're considering only half and the flow is symmetrical between the y-axis, that's why there's no flow out of this symmetry plane. Okay, you need to consider it, and you need to check like this kind of symmetric problems and its properties. Okay, so since there is no flow out of this region of this control surface or control volume, that's why there is no need of applying an additional with a factor of 2. Okay, so
Yes, sir.
you get U equal to Vx by B. So C is correct, I guess. Okay, and again.
Yes, sir.
Okay, so question number 2. Choose the correct expression for the x component of acceleration of a fluid particle in the gap between the surfaces. You need to find Ax.
So B.
B. Okay. So I guess you have used this equation. So U is
Yes.
again given Vx by B, and del U by del x will be given by V by B. So this will give V square x by B square. Okay. Yes, this is right. Okay. So again, third part of the same question. So I can just take the question and you can just repeat it. Like you can just look at a diagram again. I'll just square it up. Neglecting the variation of pressure in the y direction, the pressure distribution in the gap Px is given by, these are the expressions, and assume pressure at x equal to L to be atmospheric pressure. Okay. So these are the assumptions that they have asked us to take. So P here only is a function of x, and P is not a function of y. So this would help us to simplify the integrations, because the function is now only a function of x. So instead of using partial derivatives, now you can take the pressure gradient as a complete derivative in terms of x. So these are the clues I am giving. So keeping that in mind, you can solve the governing equations and try to obtain an expression for distribution of pressure in the gap, which is a function of x only, since they have asked to neglect the pressure variation in the y direction. So this could be a bit lengthy, so you can take your time, then we can just discuss, and I have also solved it, so we can just compare our answers. So yeah. So just as a out of curiosity, which equation do you think you would use to obtain it?
So Bernoulli's equation.
Steady or unsteady form? Okay, you can do it.
Using steady form would be easier. I got option A as the answer.
Option
But
A.
I think it should be.
Okay.
I got option A using steady form, but I think it should be unsteady form. Sir.
Why do you think it should be unsteady?
Because we are pushing the plate downwards.
That I understand, but have they mentioned that the velocity of the plate is varying with time?
No.
And we are inherently taking it to be constant while deriving the expression for u, and if you have derived the expression v also, you will see that you take the velocity as a constant, right? So even if you take the unsteady form, because I also started initially with the unsteady form, but even if you take the unsteady form, you'll find that v is only a function of x. So, and since we're only considering along the x direction, so only a function of x, so the del v by del t term will already get cancelled out, right? So keeping that in mind, that term will inherently go, and also because they have not mentioned that the plate is accelerating, and they have given a constant value, you can say that the flow is steady, because even if this is being squeezed, it is being squeezed at a constant velocity, right? So the flow is inherently constant if we are considering the unsteady form of Bernoulli's equation, because del v by del t term will get cancelled out, right? Is it clear?
So the velocity term.
Yes.
Will it get cancelled out, the velocity term?
Okay. See, let's get back to the equation. Yes, this is the unsteady form, right?
Yes, sir.
Yes. So what is the velocity that you have considered? V is the x velocity, I guess, right?
Yes, sir.
Yes. So
Vx by b.
okay, v is equal to vx by b. So is it, if we derive it with respect to time, what would be its value be?
V by d into dou x by dou t.
It is partial derivative, right? Dou x by dou t would be 0, right? It is not.
Yes, sir.
Yes.
Yes, sir.
Yes. Then this term would be equal to 0, right?
Yes, sir.
Yes. Then this inherently becomes a constant, is in a steady Bernoulli's equation, is a steady Bernoulli's equation. Then you can directly apply the steady Bernoulli's equation and you will get the answer. Okay, you need to be careful while considering the partial derivatives and the complete derivative. So yes. So once you apply the steady equation, because this is the final form that I obtained, but in my rough notebook also when I have tried, initially started with an unsteady term, thinking that it may be required, but once I solved it, I understood like why it was not required. So it is right. So answer A, it is a similar expression. So answer A is correct. Okay. This is an interesting problem. So I insist you to be very careful while approaching it, because it was very difficult for me. So okay, to model the velocity distribution in the curved inlet section of a water channel, the radius of curvature of the streamline is expressed as r equal to L r naught by 2y. As an approximation, assume the water speed along each streamline is v, capital V. Find an expression for the static pressure at the tunnel wall at y equal to L by 2 in terms of the center line pressure Pc at y equal to 0. This term basically means is that P at y equal to 0 is equal to Pc. So I guess it may help you to as it may turn out to be a helpful boundary condition. So if you solve the Gauni equation, so it may turn out to be a helpful boundary condition. So keeping that in mind, you need to find the pressure at the tunnel wall. Okay, just asking out of curiosity. Directly looking at the question, do you think the standard from the Euler's equation that we get, say in the Cartesian coordinate system, would be applicable in this problem?
It would be difficult, sir. No, sir.
Yes, I guess I cannot say that it won't be directly inapplicable, but you need to do some certain coordinate transformations so that you can take into account the curvature of the streamlines, right? So I guess the helpful idea would be to jump to the the Euler's equation of motion in the streamline coordinate system. So given that hint, I guess you can approach in that fashion using those governing equations. So that is the one hint. You can use the Euler's equation in the streamline coordinate system and then take the necessary assumptions. Okay, so you can take that as a hint and then approach. What is R here? Capital R.
Radius of curvature of the streamline.
Yes, that's correct. So keeping that in mind, I can guess then you can obtain the centripetal acceleration, the acceleration term, if you are considering the in the normal direction of the streamline. So because they are asking you to derive obtain the pressure at y equal to, so you're basically being asked, and since you know the pressure here it is equal to pc, you know that you need to deal with the variation of pressure along the normal direction, right? So I guess the equation of motion, or the Euler's equation of motion along the normal direction of streamline would deem to be helpful. So you can approach in that manner. Okay, we can wait for a few minutes and then just see. Are you able to approach the problem? Some progress?
Yes, sir. I use the normal equation dou p by dou y
Okay. Dou p by dou y.
is equal to minus rho v square by r.
Okay. Interesting.
Where r is given.
Okay. So you substitute it here, right?
Yes, sir.
So what? Okay, then I must say it's very impressive. You have obtained this equation. This was I was not able to obtain myself, but still good. So okay, then you can approach a bit further and just tell me the final answer. I guess that would be good. If it already obtained, that's fine. But if not obtained, just try to integrate it. Okay, just try to integrate it and tell me the final answer.
Sir, D, fourth one.
D. Okay. Let me check. I also don't know. So yes, it is correct. Okay. It's very impressive. Okay, but I just wanted to know how you obtained this equation. Can you throw a bit light into it? Like how do you obtain this form? Like initially, I guess you started with del p by dou p by dou n, but how do you obtain dou p by dou y? Like how you approach or reached it up to this point? Like could change from the normal coordinate from the normal direction to the y coordinate. So could you please tell me?
Sir, initially I took dou p by dou r, sir.
Dou p by dou r.
Yes, then after the clues which you gave, using that I took dou p by dou y.
Okay. Why? Like,
I took y because it was easy to integrate.
that's too. And okay. Even if you have taken y, then how a negative sign came into the picture? Like, I guess it is dou p by dou n is equal to rho v square by r. I guess this is the actual form, but how do you obtain the minus term in the equation? Because the minus itself is plays a very important role. Because if it becomes positive, then your answer is wrong. So how do you obtain the negative term? The negative sign, yeah, basically. Feel free, that's fine. You might have taken some approximation or some at least some vague idea by which you have thought that maybe negative sign makes more sense. Why? Just tell me that.
I it might be wrong, sir, but
Sure.
I thought centripetal acceleration, it should be away.
Away from where?
Like it will apply a reaction in the opposite direction.
Centimeter action should be this side or this side? One or two?
It will apply a reaction in the opposite direction, the two direction.
Uh, what would apply the reaction? The fluid.
The
Okay.
pipe will apply.
Oh, no, I understand. Tell me about the fluid because the because of centripetal acceleration, where the fluid will try to move towards one or two.
Towards the center.
Towards one, right? That's fine. And you're saying that because of this, since the fluid is pressing towards this pipe would exert an direct centripetal force. You're just saying a reaction force in the two directions, so it will be negative. The thing is, okay, pressure distribution. Okay. See, the concept is right, but the way by which you have obtained the negative sign, I must say, like, say sometimes happens is right. Your answer is right, but your approach to obtain the answer might be wrong. It might happen sometimes, right? So the thing is that in this case, all of the things that you have done or approximated has got you to the final answer that is correct. But the thing is that the key concept behind here is the coordinate system that you take. Okay, how the coordinate system comes into picture and how the change in the direction of the coordinates modifies the equation in a certain manner. Okay, is it clear up to this point?
Yes, sir.
Okay, so let me take you to my answer. I can show you here also, that's fine, but I can show you here because I can show you here also because since you have already obtained the correct answer. So yeah, so the thing is that, do you understand this symbol? What does it mean? Because they won't give this crisscross line without any meaning, right? It should have some meaning.
It means it is.
I'm sorry, it is. Okay.
Hello, sir.
Oh, I'm sorry. Okay, I just lost my connection, so I'm trying to reconnect. So, just wait for. Okay, I'm just trying to connect my screen. Okay, I just lost my connection in my laptop. So,
Okay, sir. Okay, sir.
Okay, that's fine. Okay, I guess I'm back. So yeah, just wait for a while. Okay, yes, you can resume. Yeah, please. Yeah, yes, the symbol.
Sir, that dash, that zigzag symbol, it means that the center is not here. It's far away.
Okay, yes. So I guess it is called a jagged line, if I'm not wrong. So this basically means is that the center is too far away from what is being actually shown in the diagram. So it may be very far away. So I guess Professor Chakraborty has mentioned in his lectures also, but I would again like to repeat, like if the center of curvature is too large, okay, if it's too large, you can ideally approximate the flow to be the streamlines to be approximately to be straight. Do you recollect that approximation? If there,
Yes, sir.
yes,
As art and infinity.
yes. Okay, so that's a very important assumption here. And here what they have done is, like, just to show the curvature of the streamline, they have exaggerated the curvature, but you can also see here clearly if r is 2, and here also this diagram also, just to show you that r naught represents the radius of curvature of the this pipe, not the streamlines, but this pipe, they are showing the radius of curvature is r naught, and radius of curvature of the streamline, a particular streamline, the here r is a variable, so radius of curvature of a particular streamline varies with respect to the center of curvature of this pipe, okay, which is too large. So I need to write it, I guess. R is very large than 1, just the standard value. So yeah, so keeping that in mind, we can ideally approximate that the streamlines are approximately parallel, okay, but not absolutely parallel, because you need to, because they're asking that there is a pressure variation because of the curvature of the streamline. But since r is too large, we can assume that the streamlines are approximately approximately parallel. Okay, this is first assumption. So keeping that in mind, what I say is that now since this is my geometry, what would, if this is the curvature, say this is the curvature of the streamline, and this is given by this, so what would be a normal direction here? Would it be here or here, upward or downward? Am I audible? Yes.
So if we take it as straight line, then it will be
No. Now,
bidirectional.
yes, no. Don't take it a straight line right now. I'm just saying it. For an assumption, you can say it like that. But I'm just saying, if there is a curvature, and now we are saying that now we are dealing with the streamline coordinate system, and now there is a normal direction to the with respect to the streamline. So given this curvature of the streamline, what would be a normal direction? Say 1 or 2. You can recall. Yes.
So top one.
This one. Right?
Yes, sir.
Yes. Okay. So here this is wrong. You need to consider this one as normal direction. Why? Because you can clearly see in the notes also where Professor Chakraborty has taken the normal direction. See, this is the curvature. Okay. And with respect to here only, you will have a radius of curvature r. Okay. And a normal direction outward to the radius of curvature of the streamline will give the normal direction with respect to the streamline. Okay, so it should be the outward normal instead of the inward normal. Okay, so keeping that in mind, this one should be the direction of the normal. Okay.
Yes, sir.
Okay, right. Yes, first thing is done. First, you are correct. So again, like, if I draw with different color, say Yeah, this is n cap and this is s cap. See, okay, so zoom it a bit. Okay, this is n cap and this is s cap. Okay, right. It is clear to this point, right?
Yes, sir.
Yes, sir. Okay. Now what I said is that the streamlines can be assumed to be approximately parallel if R is too large. Okay. So keeping that picture in my mind, can't I assume that my streamline coordinate system approximately, not 100% sure, but approximate, as an approximation, I can take my streamline coordinate system to vary like this. Can't it be an approximation?
Yes, sir.
Yes. So keeping that in mind, where do you see, like how do you see the normal direction, the normal vector to the streamline varies with respect to y, the y coordinate? Directly opposite?
Negative y. Yes, sir.
Yes. So this would basically mean that if I consider this equation now, del p by del n would basically give me minus del p by del y. Is it correct?
Yes, sir.
Okay, again I need to mention it, approximation, because just saying, like, if you would have taken this coordinate system, then you would have required, you would have had to obtain say the value of theta here, then do the obtain again, if this is the case, then theta, then again find the normal, then do the certain using with the help of trigonometry, obtain the value of y and x in terms of n and s. You would have had to do a coordinate transformation to get the expression of del p by del n in terms of del p by del y. Okay, if you would have considered the curvature to be like r to be to be a finite length or a small length, then you would have had to do a coordinate transformation to obtain this. Okay, but since we are taking into approximation that r is too large and streamlines can be ideally given considered to be parallel, that's why as an approximation we are saying that n varies in the opposite direction as the y coordinate, and that's why we are saying that del p by del n is equal to minus del p by del y. Is it clear up to this point?
Yes, sir.
Yes. So just as previous one, what we basically do is now we just substitute it here in this equation, in equation 1, say in equation 1. So we obtain it as a del p by del y. So we take negative sign to opposite side, it becomes minus rho v square by r. And as you rightly pointed out, since now we need to integrate as a function of y, that's why we need to change r in terms of y, which they have already given. So it becomes minus rho v square L R naught, all terms are constant, and 2y. So v is also constant because they have mentioned it that the v remains constant along all the streamlines. And if they would have said that v is a function of r, then you would have again required to transform v of r to v of y. Okay, that's also essential. But since they've already mentioned that v is constant, that's why you can take it out of the integration sign and do the necessary integration. So after doing the integration, you get the final expression as this, and you need to use the boundary condition to obtain the value of f of x, right?
Yes, sir.
Yes. So keeping all this in mind, you finally obtain the final expression as this. Okay. So is it clear, like what are the certain assumptions that you have taken, how it is an approximate answer rather than an exact answer? So I need to know that this is clear. It's clear, right?
Sir.
Okay. Yes.
I got it that dou p by dou n is equal to minus like why it is written as dou p by dou n is equal to minus dou p by dou y.
Okay.
Regarding the top equation, so dou p by dou n is equal to rho v square by r. There should it be minus or plus?
It is plus. I have written it myself, right? If I'm not wrong. Yes, this is plus because this is also minus, this is also minus. It cancels out, it becomes positive, right? Minus, minus.
Oh, okay, sir.
Okay. Is it clear, right?
Yes, sir. It's clear, sir. Thank you, sir.
Okay, sure. Okay. Then we look at the next question. So this is 5, I guess. Okay. It's very simple again. A pitot tube is inserted in an airflow to measure the flow speed. The tube is inserted so that it points upstream into the flow, and the pressure sensed by the tube is a stagnation pressure. The static pressure is measured at the same location in the flow using a valve pressure tap. If the pressure difference is 30 mm of mercury, determine the flow speed. Assume the density of the air to be 1.23 kg per meter cube and the specific gravity of mercury to be 13.6. It's again a very simple question. Directly substitute the values in the Gorny equation that I guess Professor Chakraborty has given in the notes. Just substitute the values and you'll get the answer directly. There is no requirement any rigorous manipulation to the Gorny equations. Direct substitution of the values. So I'll give you a few minutes to do that, and then you can just tell me the answer. Apply the Bernoulli's equation, then you need to substitute the value of P1 minus P2 in terms of the densities of the fluid, and after doing that, here the fluids are mercury and air, I guess. So after doing the substitutions, you'll directly get the value of velocity. Like wherever you have kept the point, you will get the velocity at that point, and that will be the answer. So please do the necessary substitutions. Answer is very simple, I guess. Just look back at your notes. That would be my suggestion.
So 80.8.
Yes. So I guess I don't need to tell how you obtained it. It's very simple, right? But still, since others may not know, I will just quickly go through the solution. So it was simple, right? I'm asking you, like, there's no rigorous calculations.
No, sir. Two-step calculation, sir.
Yes, thank you. So this is a diagram. I'll just revisiting it so that others can refer the video for solving if they do not know. So the density of the air and mercury is mentioned here. Then we apply the Bernoulli's equation in between these 2 points. Okay, I guess you have also chosen the same, and one is directly at the inlet of the pitot tube, and since we know that at the end of the pitot tube the velocity of the flow becomes 0, like we can approximate it to be approximate it to be 0. So keeping that in mind, V2 becomes 0, and we get we can obtain V1 in terms of P2 minus P1, and from looking back at the notes, we obtained that P2 minus P1 could be obtained by using this expression, rho m minus rho m by rho minus 1 into delta H, after doing certain manipulations, where rho m represents the density of the heavy fluid, that is mercury in this case. So substituting those values in this expression, we finally get the value to be 80.67. So I got 81.67 because the certain values that I have taken. So some might take some other values, so they can get accordingly. So it is approximately equal to 80.8. So I guess option C is the correct answer. Okay, so now we look at the question number 6. Okay, water flows from a very large tank. It's very important, very large tank, through a 5 centimeter diameter tube. Okay, it's better I assume, yes, through a 5 centimeter diameter tube. The dark liquid in the manometer is mercury. Estimate the velocity in the pipe. So we need to estimate the velocity of fluid in the pipe. Okay, it's very straightforward. Again they mention it. Assume the flow to be inviscid, so no need to apply any additional coefficient of discharge terms. I guess you don't need to apply obtain the mass flow itself. So I guess very simple. Again I would request you to go back to your notes. It's a bit more involving than the previous problem, since it requires you to be very clear regarding the concept of manometry, the principle of manometry, and how they apply, how to balance the pressure with respect to a given datum or the datum that you have considered. So keeping that in mind, if you're clear with the concept of manometry, you will get the answer. So and of course the Bernoulli's equation. So keeping these concepts in mind, you can approach the problem. Again, it's simple, so you can take some time and tell me the answer. So any progress, like are you stuck somewhere, or like you're trying to get the answer?
Trying to get the answers, no?
Okay, sure, please. Thank you.
Sir, I'm getting 15, sir.
15.
15.
15. Okay. I guess it's not correct because since it's not one of the options. But still, I guess you would have tried the right approach, but you would have like missed some of the steps somewhere, right? Or missed some of the important approximations or in between. So could you please tell how you started so that we can just sort out the issue?
So first, I calculated the pressure at 2 points in the manometer. One point I took at the manometer opponent and other in the pipe.
This, I guess.
Yes, sir.
Okay, so we write the boundaries equation. Sorry. We write the boundaries equation, or we find the pressure. We try to optimize.
I found the pressure, sir. I equated the pressure.
So tell me this P1 plus
P1 plus 1000 G into 0.75.
1000 into 9.81 into 0.75. Okay.
Yes, sir. Is equal to atmospheric pressure
Plus
13.6 into 1000 into G into 0.15.
okay. So given that you know the value of PA, what do you obtain P1 as?
PA plus 1000 into G into 1.29.
Okay, what's the numerical value? Tell me. P1 is equal to
Atmospheric pressure plus 1290 G.
1290 into G.
Yes, sir.
Okay. Let's see what it is. Okay. I also don't know. Let me see. Just wait. Okay. So this 1290 into 9.81. So it comes around PA plus 12655 Pascal. I will just write PA so that it's not confusing. Okay, this is actually correct. This is actually what I exactly got. Okay, then what you do?
Sorry. Then I applied Bernoulli's equation at the open end of that flow where flow is taking place.
Say it is 3. So you write a Bernoulli's equation, right? So I will write P3 by rho g plus V3 square by 2g plus Z3 equal to P1 by rho g plus V1 square by 2g plus Z1. Okay, so what are the approximations that you have taken?
Sir, one doubt, sir.
Okay.
Like I took instead of at the top 3, I took downwards, sir, as point.
This one.
I took that point and one more point I took at the outside where flow is happening outside.
Here.
No, sir. Flow is yes, sir, that one I took. Is it wrong?
See, it's not wrong because the thing is, you can assume that there is one streamline from here, from this point to this point, but because since you don't know the exact equation for the velocity field and you cannot ideally calculate the vorticity, so you can assume that the streamline lies from here to here. Okay, that's first point. But here you don't know what is the velocity of the flow at point 3, right? Do you know it?
I assumed it as 0 because the tank is large.
That's again the issue, right? You cannot assume it to be 0. Even if the tank is large, this point is very close to the exit or very close to the exit of the tank, right? and there must be a velocity that there would be a suction velocity that would suck the fluid out of the tank, and that's why the velocity at this point cannot be equal to 0. Okay,
Okay, sir.
so this is where I guess you have done it wrong, and it's actually a huge, it's a, and again here what do you know, like you know, I guess it is P equal to PA, I guess. Then what is the velocity?
Velocity to be found out.
Okay, oh I'm sorry, velocity to find out. Okay, that's fine, but here again there are two unknowns, right? You don't know the pressure here. Pressure you can obtain by the hydrostatic law, I guess, that's fine, but velocity you don't know, so that becomes a challenge, right?
Pressure at that point I took what I found out, sir, P1, because pressure will not vary in the x direction.
This one, right? Yes, again, but I don't think it would exactly be the same, since I guess there should be a additional pressure because of the height of the fluid here. That's how I feel, but not it should, there must be an additional pressure here because of the height of the fluid, right? Even if it is along the same direction, but still again this is not exactly the same geometry. Okay, since again if if it would have been a simple tank instead of having an orifice at the exit, you could have ideally approximated that the point 3 and point P1 equal to P3. Okay, but since there is suction here in this case, and the velocity at this point and this point is different, right? The flow is not stagnant. Okay, the flow is not stagnant here, and that's why you cannot accurately assume that the pressure at point 3 and point 1 would be equal. Okay, this is not a correct approximation. You cannot assume like that, even if they are at the same height, but the geometry is different and the place, the physics of the flow where the flow occurs is different. One it's ideally hydrostatic, and others there is a velocity, when others is a flow through a pipe. Okay, so given these changes in the geometry, you cannot assume the velocity pressure would be the same. Okay.
Okay, sir.
Yes, and that's why I guess it is where you have done the mistake. So let me tell you one hint, that a good practice to apply the boundary equation is at the points where you know the variables, where you know the flow parameters, where you know most of the flow parameters, because here you can see P3 is equal to PA, right? If I choose a 3,
Yes, sir.
yes, V3 would be equal to 0 because tank is very large, right? V3 would be equal to 0, right?
Yes, sir.
Yes, and the only then again, since this point is 1, this point is 3, there is an height difference, Z3 minus Z1, that will be equal to 4, right?
Yes, sir.
Yes, so keeping these factors in mind, and here also you know the pressure at point 1, you know the pressure P1 is equal to, as you have mentioned, PA plus 12655 Pascal, and only unknown remains is V1, right? So keeping these things in mind, the ideal choice of points would be at point 3 and point 1 here. Okay, these points
Okay,
I won't say these are wrong. You can apply here also, here also, but the thing is again that you don't know the exact value or accurate value. I would say like more approximately correct, I could say in that term, values of the pressure and velocity at these points. That's why it's not a good choice of selecting points for implementing the boundaries equation. Okay, so I guess just following the same, after applying the principal manometry, I get the same answer. I just obtain the absolute value of pressure. Okay, at point 2, I have taken point 2 this to be point 2, so that's why I have kept it here. So I get P2 is equal to 11390 Pascal, just to eliminate any errors while subtracting or including or excluding the atmospheric pressure. I'm just considering the absolute pressure in this case. Again, so then if we apply the boundaries equation between these 2 points, you get Z1 minus Z2 plus P1 minus P2 by rho z equal to V2 square by 2g. So only unknown here is V2. Okay, V2 is here, and V2 would be equal to at the velocity at the exit. Why?
Area is same.
Area is same and the flow is inviscid, right? As you have mentioned.
Yes, sir.
Yes. Keeping those approximations, V2 would be equal to V exit. Okay, exit. So keeping these things in mind, finally we substitute the values in the boundaries equation, is in equation 1. Then we finally obtain V2 is equal to 7.29 meter per second. Okay, you can try it after the class. After the session. So just cross the
Yes, sir.
Okay, sure. I guess we are short of time, but since we started a bit late, I guess if it's fine from you, can we take additional 10 minutes for the remaining questions? If it's fine from you, since you're only one here.
Yes, sir.
Okay, I'm really sorry. Okay, but since we started late, I need to cover the two remaining questions also. It will be over by 10 minutes. It's very simple. Okay, so thank you for your cooperation. So yes, so question number 7. I guess the diagram itself shows that it's a question on siphon. Okay, a U-tube acts as a water siphon. The bend in the tube is 1 meter above the water surface. Okay, the tube outlet is 7 meter below. Okay, they mentioned it. The water surface. The water issues from the bottom of the siphon as a free jet at the atmospheric pressure. So they are mentioning that P2 is equal to PA. Determine the speed of the free jet. You need to obtain V2. Assume G equal to 9.81 meter per second square. So I guess the question is clear. Given this geometry, I can zoom it a bit. Given this geometry, you need to obtain V2. That is the velocity at the exit. So I can say that the principle of siphon can be very well understood by applying boundaries equation at the correct points. Like they have exclusively mentioned where to apply the boundaries equation. So given that hint, you can apply the boundaries equation and see what are the values that you know and what are the values that you need to find.
So last option.
11.7.
Yes, sir.
Okay, I guess it is correct, but still, at what 2 points have you applied the boundaries equation?
1 and 2.
Okay, that only. Since here you don't know the value of, if you have taken one at point A, you don't know the velocity, right? You don't know the pressure also. So
Yes, sir.
you know at P1 equal to PA, V1 would be equal to 0, I guess you have taken, right? Yes.
Yes, sir.
Okay, and then P2 is equal to PA again, then V2 you need to find out. So only variable remains is V2 and it depends on the height difference. So keeping that in mind, you get V equal to 11.7 meter per second. So just to check it again, it's very simple again. We just apply the equation between point 1 and 2, boundaries equation between point 1 and 2. Then you obtain V2 square by 2 is equal to G Z1 by Z2. Then we obtain V2 is equal to square root of 2z Z1 minus Z2, where we obtain V2 is equal to 11.7 meter per second. So it was very simple, I guess, very straightforward. So again, the second part of the question is, the minimum absolute pressure of the water in the bend in question 7 is, they ask, this is the question, assume atmospheric pressure to be 1.01 bar. Okay, they're asking the value of the suction pressure here at point A. So I guess it's again very straightforward where to apply the boundaries equation. And okay, so given that hint, you can approach, just tell me the answer.
Sir, option B.
22.7. Yes. So again, I guess it was very simple again. So at which 2 points have you applied the Bernoulli's equation?
2 and A.
2 and A. Okay. So in my case, I guess it's also correct, but in my case, I guess I've obtained at point 1 and A. That's fine. So again, this is obtained by the Bernoulli's equation. This simplified from the Bernoulli's equation. So substituting all the values, I'm just showing my approach, but because we almost got the same answer. So keeping that in mind, we get PA is equal to, we substitute the value of Z1 and ZA, so it will become -1 because A is above 1, so that means ZA will give -1. VA we know because V2 would be equal to VA again because the area of pipe is constant. That's an approximate value, okay, we approximate it to be constant, okay, because we are not taking the loss because of the height difference, but again as an approximation we can ideally take it to be constant. Okay, so keeping that in mind, again we get PA is equal to 78255 Pascal, that is gauge pressure. Okay, then since we need to obtain the absolute pressure, I again add the atmospheric value of atmospheric pressure. I forgot that they mentioned it to us to take equal to 101,000 Pascal. I said I took the exact value, that's why I got a slightly different answer, but by the exact similar approach you get the same answer if you apply the equation at point PAN at AN2. So I guess use the same equation, right? Just the points you have changed.
Yes, sir.
Okay, so keeping that in mind, you get the similar answer. So option B is correct. Okay, so final question. Again, it's a, I won't say it's difficult, but you need to know the form of equation, the special form of Bernoulli equation that you need to use. Okay, compressed air is used to accelerate water from a tube. Neglect the velocity in the reservoir and assume the flow in the tube is uniform at any section. The cross-sectional area of the tube is constant. At a particular instant, the velocity of water in the tube is v, and the acceleration of the water in the tube is g by 4, where g, am I audible? I lost my connection, I'm sorry. Am I audible?
Yes, sir.
Oh, I'm sorry, I lost my connection in between. Okay, that's why I'm asking. Okay, so at a particular instant, the velocity of water in the tube is v, and the acceleration of the water in the tube is g by 4, where g is the acceleration due to gravity. Determine the gauge pressure of air in the tank if H is equal to L by 8 at that instant. So is the question clear?
Yes, sir.
Okay. I would just give one very simple clue, is that you need to apply a special form of Bernoulli's equation, and I guess by now you know which one to apply. So keeping that in mind, this time the velocity is not constant. They have mentioned that the velocity is varying because the flow is accelerating at the tube. Okay, they've told that the flow is accelerating at the tube, though the flow is assumed to be constant at the large tank, large reservoir. So since the flow is accelerating at the tube, you need to take into consideration the unsteady term. So keeping that in mind, you can approach the problem and just tell me the answer. Am I audible?
Yes, sir.
I'm sorry again. Okay, I just lost my connection. That's why I'm asking again and again. So yeah, you can continue your answer. Sorry. So, did you get an idea how to approach it?
Using Bernoulli's equation, sir.
Or steady or unsteady flow?
One unsteady flow.
Okay, okay, that's fine. So, okay, I guess the approach is correct. So you can just take a few more minutes and tell me the answer that you got. So.
Hello, sir.
Yes.
I am getting the answer which I am getting is not in the option, sir.
Sure, no problem. But just tell me the answer. That's fine.
I am getting rho into v square by 2
V square by 2
minus
minus
3gh by 4.
3gh by 4. Okay. Have you taken this approximation?
Yes, sir, but I took ds as h.
DS is H.
H.
Okay, so what was your streamline? Say S is a streamline, so you have taken DS as H. So what were your 2 points that you have considered?
One at the free surface and one at the open end, the tube end.
Okay, so say this is 1 and this is 2. Okay, right. Is it so?
Yes.
Yes.
Yes, sir.
So we can say the streamline is of this form. Okay. Is it? Is it so?
Yes, sir.
Okay.
Yes, sir.
Then if we assume that the length is much larger than h, that's I'm assuming, then we can neglect this part of the streamline, right?
Yes, sir.
Then we can take the ds should be ds should be ideally equal to L. Integration of ds from point 2 to 1 should be ideally equal to L.
Yes, sir.
Yes. So I guess why did you consider it to be h? Like what was your assumption to take it as h? Have you considered the tank to be very large so that h is much larger than L, like that? Have you taken it to be this case?
No, sir. What I thought was that since water is flowing from H to downwards, I thought that L should be neglected because that H1 only should be considered. H only should be considered.
Yes, but the
I thought
streamline,
it like this.
but streamline would extend from the point that you have considered to the exit, right? And since we don't
Yes.
know whether the flow is rotational or irrotational, it is advisable that you choose the points to lie along the same streamline, right? See,
Yes, sir.
this Bernoulli's equation or the problem that you are solving does not necessarily give you a very highly accurate answer, but it gives you a very like approximate idea in a manner that you know how the flow behavior changes if the certain flow parameters are changed, right? It is not necessary that the streamline that I have considered is what is absolutely correct. There might be some uh, vorticities here. There might be some additional bends in the streamline. It might happen like that, or it might happen that the what I'm trying to obtain is not accurate, 100% accurate. It may be even 60 or 70% accurate, but it gives you a vague idea how the flow parameter varies when certain how the flow changes when certain flow parameters are varied. Okay, so keeping that in mind, if I take the streamline in this manner and given the assumption that I take that L is much larger than H, we can take the length of the streamline to be equal to L. Okay, this is a very important assumption again, because we are neglecting this part of the streamline. Why? Because you're taking L to be much larger than H. Is it clear?
Yes, sir.
Yes. Okay.
Okay, sir.
Okay. So I guess it's a bit long, so I just try to show you the solution that I've done. So yeah, this is the diagram again. And acceleration, they've told that the flow accelerates in the tube, okay, not the tank, in the tube with an acceleration equal to g/4. So ideally we use the unsteady form of the equation because the flow is changing at the tube, that is at the section 2. So not section 2, the point, since we have considered a point to be at the exit of the tube, and since the flow is accelerating at the point 2, that's why you need to take into consideration the unsteady term also. So keeping that in mind, again we neglect the velocity because they've told that the velocity of the flow at the tank should be is equal to 0. So we neglect the velocity. Then P2 at the exit is equal to atmospheric pressure, so we we disregard it again. And then because like it will basically give us even if we include it will give us the gauge pressure. We are trying to find the absolute pressure, right? So we are trying to find the gauge pressure because P1 basically means P1 plus PA if we are considering it to be in absolute case. So keeping that in mind, we neglect the atmospheric pressure, and then we get this form of the Bernoulli's equation, because this is the assumption that we take here. So dv2 by dt would be what would that be?
G/4.
Because they've asked us to find the pressure at the instant where the acceleration at the tube is acceleration of the fluid at the tube is g/4, right? That's why at the instant we use dv2 by dt is equal to g/4. Then substituting that value, we get the equation of this form, and you get right why we used h, because Z1 minus Z2 would be equal to H, right?
Yes, sir.
Yes, so keeping that in mind, P by rho G plus H equal to V2 square by 2 plus L by 4. I guess it is looking like C, so let me be clear, becomes L by 4. So for they've told us to find the value of pressure when the height of the height of the water at the tank is equal to L by 8 at that instant, right? So we substitute the value of H is equal to L by 8 in the equation, then we get that P by rho G is equal to V square by 2 plus L by 8, and then again we uh, take rho into the right, rho by rho G term in the right hand side, then we finally obtain this equation. But again, L by 8 is equal to H, right? From here we just substitute back
Yes,
the
sir.
value of H, then we get that P equal to rho V square by 2 plus G by H. So option C is the correct one. Is it clear?
Yes, sir.
Okay then, thank you. I'm really sorry that I exceeded beyond the stipulated time, but since there was a bit of internet disturbance in internet connectivity, and also we started the session a bit late, so I hope you understand. So again, thank you. So I request you again, I ask you to join the session for next week also. So, and I guess it was fine. Okay then, thank you so much. Okay,
Thank you, sir.
thank you.